All right, hello everybody. So we're going to finish up our last little chunk of notes that we had from last week. So make sure you get your notes out ready to run through it. So last week we finished off on talking about orbits and the different orbit patterns that there are. So whether we're talking about comets and how they are the ones in red here that seem to be a little more narrow, more oval shaped compared to the comets that are a little more rounder, and then the planets' orbits around the sun are a little closer to circular, but also a little more oval shape. And you can see where they are traveling closer or farther away from the sun and where they generally like to follow in orbit. So with that, we get into orbital data. So comets generally have orbits of larger size and greater eccentricity than those of asteroids. Typically, the eccentricity of the orbits is 0.8 or higher. According to Kepler's second law, therefore, they must spend most of their time far from the sun, moving very slowly. As they approach perihelion, the comets speed up and whip through the inner parts of their orbits more rapidly. So we could see here in the data chart above is the more eccentricity there is, the more circular those orbits are going to be. So for example, the closer to zero they are, the closer they are to being perfectly circular. The farther away they are, the closer to one, the more oval shape they're going to be. So we could see here that Venus has some of the most like eccentric or more circular patterns. Same with Neptune as well. But we can also see when we get to Mars or Mercury, they tend to have more of an oval shape as it's uh, traveling around the sun over time. So with that, we talk about firing if we were on top of the Earth and we could stand there and shoot a bullet, and we could actually see what would happen and how does the orbits happen. So if we're looking at picture A here on the left, both A and B, the velocity is not enough to prevent gravity from pulling the bullet back down to Earth. In case C, the velocity allows the bullet to fall completely around the Earth. So if we did not have gravity, it would follow point C, where it would just continue in a circle around Earth. Well, unfortunately, or fortunately, we have gravity here on Earth, so it's going to behave more like A, where it's going to just fall instantly back down to Earth because that pull of gravity is so strong. So the diagram by Newton is his addition or kind of idea of gravity and the orbits around them. The more gravity there is, the more faster they're going to be pulled down to Earth. The less gravity, the more circles that can actually happen within that orbit. And that's because the further away, the less gravitational pull, the slower they're going to move. And so they're just going to continue in that orbit. So because of that, we have a lot of satellites that actually orbit Earth. This figure shows the largest pieces of orbital debris that are being tracked by NASA in Earth's orbit. So this is a slightly older picture or like demonstration of what that would look like. And there's probably a lot more to that now. So every little dot here is a satellite. So we have hundreds of thousands of satellites up in our atmosphere or up above Earth's atmosphere right now. And they just kind of hang up there and will travel around the Earth and keep moving around, just sending data, collecting data. Each one does its own thing. So a lot of our phone signals go up to satellites up on outside of our atmosphere, and they just hang up there. Eventually, they do slow down and they do come down into our atmosphere. And when they do, they generally will crash back down into Earth. So NASA keeps track of them so that we can keep an eye on where they're at. And if they are going to crash into the surface, we know exactly where it's going to be at, and we can either try to send a rocket to help it break down, or we can see if it's going to hit the ocean so we can collect it and get data from it. So a lot of times we have these modern computer inputs. So we call these the supercomputers at NASA. So their AIM Research Center are capable of tracking the motions of more than 1 million objects under the mutual gravitation. So these, if you've ever seen the movie Hidden Figures, this is their job. We have now computerized that, but they're there to calculate where these objects are in its orbit around Earth so that we can keep track of them and make sure that things aren't going to crash where they're not supposed to and hurt people, or we can see where it will crash and we can actually recover it and collect some data from it from there as well. Okay, and then the mathematicians who discovered a planet, so John Couch Adams and Urbain J.J. Elverer, share the credit for discovering the planet of Neptune. They both worked together on that, or more like John had their first idea, and then Leverrier, he came in later to try and figure out and finalize and clean up his data about Neptune. Obviously, it was so far away we couldn't use telescopes to see it, but we had theorized that they were there. Real quick, we're going to watch this video about the discovery of Neptune.
Hi guys, and welcome to Brain Snacks. My name is Clara, and in this channel I would like to share my fascination about science and technology. The first episode is about the discovery of Neptune. There are just a few places on Earth from where a planet was discovered. Recently, I found out that I used to live close to the discovery location of Neptune. Neptune was discovered in 1846 by the German astronomer Johann Galle after the French mathematician Urbain Le Verrier calculated where to find it. Let's see what's left of the observatory today. Now I'm standing close to the exact location where Johann Galle looked at the night sky through his telescope. Right behind me, that's the Jewish Museum, and this building already existed at the time of the Berlin Observatory. Unfortunately, of the observatory itself, there's nothing left today, except for an information panel with the ground plan and explaining that on the wall of the observatory there used to be a reference benchmark for the sea level. This is how the Star Observatory looked at the time when Neptune was discovered. Here we have the astronomer Johann Galle and the mathematician Urbain Le Verrier. But I think that everyone should know that from here a planet was discovered. We should put a flag here. But wait, didn't I bring one? But before we find out how this actually happened, here's some facts about the planet. Neptune is the farthest known planet from the Sun in our solar system. It is the fourth largest planet by diameter after Uranus, Saturn, and Jupiter. Neptune is 17 times as massive as Earth, and 58 Earth volumes could fit in it. Its average distance from the Sun is 4.5 million kilometers. One Neptune day is 16.1 hours, and one Neptune year, so the time that Neptune needs for a whole orbit around the Sun, is 164.8 years on Earth. This is NASA's spacecraft Voyager 2, the only spacecraft that visited Neptune and took close pictures of it and its satellites. Neptune has 14 known moons. Triton, its biggest moon, has some very interesting characteristics. Its orbit goes in the opposite direction of the orbit of its planet. This is called a retrograde orbit. Moreover, the orbit is inclined relative to Neptune's equator, which suggests Triton did not form in the orbit around Neptune, but was gravitationally captured by it. But how did the mathematician and the astronomer discover the planet? Well, long before they did, already other astronomers like Galileo Galilei had seen Neptune through a telescope, but they didn't identify it as a planet. The actual discovery started with another planet, Uranus. In 1846, it was known that Uranus, the closest planet to Neptune, had irregularities in its orbit around the Sun. The theory to explain this of Urbain Le Verrier was that there had to be another planet farther out in the solar system that influenced Uranus gravitationally. With the data of Uranus' orbit, he calculated where to find this unknown planet. Then he informed Johann Galle in Berlin, who discovered Neptune within 1 degree of its theoretically calculated position. This makes Neptune a planet that first had been theoretically predicted and then had been actually discovered. Isn't that cool? Thank you very much for watching, and if you liked it, please hit the Neptunian.
Okay, so with that, so that was a little bit more about Neptune and how it was discovered. So with the ellipse, so we construct an ellipse by pushing two tacks into a piece of paper and by drawing a board and then looping a string around the tacks. Each tack represents a focus of the ellipse, the two tacks being the sun. Stretching from the string tight using a pencil, then moving it to the pencil around the tacks. The length of the string remains the same, so the sum of the distance between the 2 points of the ellipse and to the foci is always constant. So basically what that's saying is we will, to be able to figure out what the ellipse would be, again, the sun is never directly in the center of our orbit or our ellipse around the sun. It's always off to a foci, so either point on either side. So we can see where that is going to stretch further away or be closer depending on where we're at in our rotation around the sun. Okay, so that's all I have for today. Again, super short and sweet. So for the rest of the period, you can work on your Starry Night constellations and star lore. The sub will have the packets for you, or should have already handed them out. So the rest of the time is for you to work on that. The Starry Night will be due tomorrow when you walk in. So if you have any questions, please let me know. Shoot me an email, and I will try and get back to you as soon as I can. Have a great rest of your day. See you later.